Hello everyone, in this video I'm going to be talking about how the heartbeat is coordinated by the SAN, the Sinoatrial node or pacemaker, and the AVN, the Atrioventricular node. Now it's more than just touching upon the structure of the heart or the cardiac cycle and where blood goes to and from, as I've done in previous videos. This is actually what controls that blood flow. So how the heartbeat is initiated and what determines when part of the heart can contract. And included on this front slide, this graph that I have here is from an ECG, an electrocardiogram, and it measures the electrical activity of the heart. So I'm going to be talking about this very classic picture, because many people, or many of my students, recognise this, but don't necessarily appreciate what each sort of crest or trough on this particular graph represents. So that's what we're going to talk about in this video. Now for this video we're going to be using this picture as our basic outline of the heart, and we can see it has numbers 1, 2, 3 and 4 on it with a few arrows. I'm going to talk through each of the arrows and what those stages represent. So let's think of our starting point as being atrial systole. So that's a period when the atria are about to contract. So we're going to imagine that these top two chambers that I'm just labelling here, the right atrium and the left atrium, those two chambers are about to contract and push the blood down through the valves into the ventricles. But we're not thinking about blood flow, we think about, ultimately in this, it's going to be a nerve impulse. So the starting point is this patch of cells in the right atrium called the sinoatrial node. Patch of cells called the natural pacemaker. Now, some students may have heard of artificial pacemakers being fitted as a result maybe of injury, a heart attack, myocardial infarction, of disease, those kind of things. And you can indeed have an artificial one fitted, but this is our natural pacemaker, and this is what is going to trigger the heartbeat ultimately. So we have this patch of cells, right atrium, called the sinoatrial node, that will initiate a nerve impulse. So in number one, what we basically have is a nerve impulse generated by the SAN, as it's abbreviated, the sinoatrial node. Now, I should say that the heartbeat is thought of as being myogenic. That's myogenic, myogenic. And what it means is it has an inherent heartbeat within it, as in those cells can initiate that nerve impulse from within themselves. They're not relying on any external stimuli or nervous control. Now, I should say that the pacemaker does have a sympathetic and parasympathetic nervous supply, and I'm not going into detail about that, but that's just to say that the pace at which it fires that impulse can be increased and decreased by external nerves. But to initiate the impulse, the SAN can do it itself. It is myogenic, it has that inherent beat within it, if you like. So the first phase, nerve impulse is generated by the SAN, and a wave of depolarization spreads across both atria. So that's really important. That's what those arrows represent. You get a wave of what's called depolarization. Now, again, I'm not going to go into too much about depolarization, but it's a way in the topic of nerves and the synapse, you learn that depolarization is the way that channels enter the cells as a means of propagating that impulse. So that's what we're going to just take it as now. We're going to take it as this wave of depolarization, or this impulse, spreads across both of the atria, causing them to contract. So as number one happens, as the sinoatrial node triggers a nerve impulse that spreads across both atria. The atria contract and they push blood down into the ventricles. Now you can see just here, we have a non-conducting layer in the heart, a wall, if you like, between the atria and the ventricles. It's this dashed line that we've got here. Now that's really important because if that electrical impulse were to spread down the atriums and they would contract and push blood into the ventricle, but then that impulse immediately passed to the ventricles would contract instantly, even if they're not full. So as they're filling with blood, that impulse, without that non-conducting layer, would pass straight to the ventricles and they would contract. So they would be pumping out blood when they haven't fully filled. It would be ineffective and actually dangerous. The heartbeat would just become irregular and you wouldn't be pumping out the volume that is required. So you have this non-conducting layer in the heart wall between the atria and the ventricles to sort of slow that impulse and to ensure that the ventricles fill fully. Then we have number 2 in our diagram. Now, number 2 represents the AVN. So number 1 we have here is the SAN, and I'll just label it here. Number 2 is our AVN. It's called the atrioventricular node. It's a patch of cells that lie between the atrium and ventricles, and it sort of helps to create a delay to allow for proper ventricle filling. And when that nerve impulse reaches the AVN, so we can see from number 1 the arrow spread across the atriums, then they almost work their way into the middle. And then we're ready to trigger the AVN. So the AVN, after a short delay, triggers an electrical impulse, and that impulse spreads down, as you can see as shown by the diagram on number 3 here. That impulse spreads down the septum, the middle part of the heart, all the way down to here, which is known as the apex or the base of the heart. So it travels down the septum to the apex of the heart. So let's just pick up with a point about the actual septum. If we imagine, I'm just going to draw a rough sketch here, what we have are lots of muscle fibres in that septum, and those muscle fibres are called Purkinje fibres. Sometimes it's seen as Purkinje fibres. This is how I refer to it, as the Purkinje fibres. Sometimes it does have an alternative spelling, but this is the one you should use. So we have Purkinje fibres, muscle fibres in that septum. Now those fibres together form, you almost imagine them being wrapped around together. Those fibres all together create what is called a bundle. And it's collectively known as the bundle of His, H-I-S, named after the scientist who presumably discovered that. So we have Purkinje fibres, individual muscle fibres, that are wrapped together to form a bundle of His. So when the AVN generates its impulse and it travels down the septum, we mean that it's travelling down those Purkinje fibres in that bundle of His to the apex of the heart. Then we have one final step, and that's shown by number 4. Once that electrical impulse reaches the base or the apex of the heart, it then travels up, as you can see by these arrows here, it travels up the walls of the ventricles. And when it travels up the wall of the ventricles, it initiates ventricular systole, or ventricular contraction. And that ultimately is how the heartbeat is coordinated. That's it, those simple steps. So number 1, the sinoatrial node, or the pacemaker, generates electrical impulse which spreads across both atria, causing them to contract, and that allows blood to be pushed from the atria into the ventricles. After a short delay, the AVN, the atrioventricular node, generates a nerve impulse that passes down the Purkinje fibres in the septum of the heart to the apex, to the base. And it passes it to the base to provide the best sort of contracting force, if you like. If the nerve impulse is going to the very bottom of the heart, when it passes up the walls of the ventricles, it can really push all of that ventricle and cause all of that ventricle to contract. So number 3, that electrical impulse spreads down the Purkinje fibres to the base. And then finally, as I've just said, that nerve impulse travels up the wall of the ventricles, causing the ventricles to contract, or ventricular systole, which will push the blood out of the ventricles into the aorta and pulmonary artery. So what I'd like to do now is just talk through that ECG, that graph, and show what those waves basically represent. So it looked a little bit like this, just doing a rough sketch. That's kind of what we had, and we said that this was called an ECG, an electrocardiogram. You could use an echocardiogram, which uses ultrasonic wave, ultrasound, to monitor the heart and look for particular defects, but this is an ECG, an electrocardiogram that measures electrical activity. And we have distinct letters for these phases. So we call this a P wave, this part here is a Q, R, S, and this is T. I just want to talk through what these actually refer to. The P wave represents that period of atrial systole. So you get that electrical activity, that P wave, when the atria contract because of the SAN, sinoatrial node, essentially. Then we have what's called a QRS complex, and this would be a period of ventricular systole. So you get this really sharp spike, the QRS complex, when the ventricles contract. This wave of electrical activity spreading across the ventricles, the walls of the ventricles, gives rise to this QRS complex. You have this region here, which I'll just highlight, called the PQ interval. Clearly that would be when the ventricles are filling with blood. Then finally we have this T wave. And this T wave and this whole part of our graph represents a period of just general systole, of relaxation for the heart. So both atrial and ventricular systole. So when the whole heart is under a period of relaxation or not contracting, and the atria are once again filling with blood, ready to then push that blood out by contracting. That's just a little bit about an ECG, and there's a lot you can tell from an ECG. You could tell whether somebody is bradycardic or tachycardic, and that means you can see whether the heartbeat is slow or too fast. General heartbeat regular is about 60 beats per minute, so we can look at and see if it's way under 60 or over. You can also, with an ECG, pick up certain iron deficiencies. You can look at myocardial infarction, as in heart attack damage, and you're able to spot damage brought about by myocardial infarctions based on the amount of electrical activity that you have in different regions of the heart. Now, I'll talk about those in another video, but this is just a very brief introduction to ECG to show you the PQRS-T waves and how they relate to the SAN, AVN, and the initiation of a heartbeat. Okay, hope all that helps.